Structure of reductive Lie algebras and Maximal Tori. An exploration of symmetry and algebraic foundations. Mathematics has long been an abstract yet deeply structural discipline, concerned with patterns, symmetries, and the fundamental relationships that govern logical consistency. Within this vast field, the study of algebraic structures forms a core component, connecting multiple areas such as geometry, topology, and physics. Among these structures, Lie algebras stand as one of the most powerful tools in modern mathematics, originally formulated to describe the infinitesimal symmetries of continuous groups. The study of reductive Lie algebras and their associated Maximal Tori is central to understanding the deep underlying symmetries that govern these algebraic systems. From a historical perspective, the study of Lie algebras began with the work of Sophus Lie in the 19th century, where he sought to develop a systematic method for solving differential equations through group symmetries. Over time, Lie algebras were found to be indispensable in multiple disciplines, particularly in theoretical physics, where they describe the symmetries of quantum field theories, particle physics, and general relativity. The classification of Lie algebras and their internal structure has since become one of the most mathematically rich subjects, influencing fields as diverse as algebraic geometry and representation theory. This documentary explores the fundamental structure of reductive Lie algebras, the importance of Maximal Tori, and their interplay in mathematical theory. By tracing the historical development, modern applications, and deep mathematical properties, this exposition aims to make accessible one of the most abstract yet structurally significant areas of pure mathematics. To understand the essence of reductive Lie algebras, one must first grasp the concept of a Lie algebra itself. In its simplest form, a Lie algebra can be thought of as an algebraic system equipped with a binary operation known as the Lie bracket, which encodes the concept of infinitesimal transformations. These algebras are particularly important in the study of continuous symmetry, as they describe how small perturbations within a mathematical or physical system evolve. Among all Lie algebras, a fundamental distinction arises between simple, semisimple, and reductive structures. A simple Lie algebra is one that is non-abelian and contains no proper non-trivial ideals. These are the basic building blocks of all more complex Lie algebraic structures. A semisimple Lie algebra is defined as a direct sum of simple Lie algebras, devoid of any abelian normal subalgebra. These algebras form the foundation of classification theorems that categorize algebraic symmetries into distinct families. The notion of reductivity emerges when we consider Lie algebras that extend beyond semi-simplicity. A reductive Lie algebra can be understood as a semi-simple Lie algebra with an additional abelian component that commutes with the rest of the structure. One of the most notable examples in this category is the algebra of all complex square matrices, which contains both semi-simple and abelian components. The study of reductive Lie algebras is central in representation theory and harmonic analysis, where they serve as fundamental tools in classifying group representations. Historically, Élie Cartan was instrumental in the classification of Lie algebras, demonstrating that semi-simple Lie algebras over complex numbers could be fully classified into a handful of well-defined types. This classification, involving the so-called Dynkin diagrams, is a remarkable achievement in mathematics, providing a complete list of fundamental algebraic symmetries. Reductive Lie algebras, in contrast, introduce a level of structural complexity that bridges pure mathematical abstraction with applicable representations in physics and geometry. One of the defining features of reductive Lie algebras is the presence of a maximal torus, a crucial concept that plays a significant role in understanding their internal structure. In mathematical terms, a torus in the context of Lie theory is a maximal abelian subalgebra consisting of semi-simple elements. The Maximal Tori are the largest possible such subalgebras within a given Lie algebra. and they form the backbone of many classification theorems. The importance of maximal Tori stems from the fact that they allow us to diagonalize elements within a reductive Lie algebra. By understanding the structure of the maximal torus, mathematicians can gain insight into the root system of the algebra, an intricate combinatorial object that encodes essential symmetry properties. The root system of a Lie algebra essentially describes how elements of the algebra interact under the action of the maximal torus, providing a roadmap for understanding its representation theory. To illustrate this with an example, consider the classical case of Gel n C, the Lie algebra of all complex n by n matrices. In this case, the maximal torus consists of all diagonal matrices, forming an abelian subalgebra that generates the decomposition of the algebra into simpler components. The existence of such Tori is crucial in simplifying complex algebraic structures, making them more accessible for computational and theoretical exploration. The significance of reductive Lie algebras and their maximal Tori extends beyond pure mathematics, finding extensive applications in physics, differential geometry, and algebraic geometry. In theoretical physics, the role of Lie algebras is indispensable in understanding the fundamental symmetries of the universe. The standard model of particle physics, for example, is deeply rooted in the study of Lie groups and their associated Lie algebras. The gauge symmetries of fundamental forces, electromagnetic, weak, and strong nuclear interactions, are governed by reductive Lie algebras such as SU, 3, for quantum chromodynamics, and SU, 2, XU, 1, for electro-weak interactions. The maximal Tori of these algebras provide insight into the possible states of fundamental particles, dictating how they interact under different force carriers. In differential geometry, the theory of Lie algebras is instrumental in studying geometric structures, such as symmetric spaces and holonomy groups. Many advanced results in Riemannian geometry rely on the classification of reductive Lie algebras, providing a pathway for understanding the curvature properties of spaces that arise naturally in general relativity and complex geometry. From the perspective of representation theory, maximal Tori play a crucial role in classifying the representations of Lie algebras. The weight decomposition of a representation is determined by the action of the maximal torus, leading to deep insights into the structure of infinite dimensional representations used in mathematical physics and number theory. The famous Langland's program, a grand unification of number theory and representation theory, heavily relies on understanding the interplay between reductive Lie algebras and their maximal Tori. The study of reductive Lie algebras and maximal Tori continues to be a fundamental pursuit in modern mathematics, bridging abstract algebra, geometry, and physics. Through the classification of Lie algebras, the understanding of maximal Tori, and their applications in representation theory, this field provides a structural lens through which mathematicians can decode complex symmetries governing both theoretical constructs and the physical universe. From the pioneering work of Cartan and Weil to contemporary applications in high-energy physics and algebraic geometry, the significance of these structures remains unparalleled. Their role in deciphering the fundamental language of symmetry ensures that the study of reductive Lie algebras and maximal Tori will remain at the forefront of mathematical exploration for generations to come.